Alrighty. Good afternoon, everybody. Thank you guys for coming to my talk on noon, or at noon, on the final day of the conference. This is the history of the GPU. My name is Nick. Before I get started, let me just introduce myself. So my name is Nick Driscoll. I work on the Vulkan SDK at Lunar G. I have 6 years of experience doing 3D graphics programming and GPU programming in general. At the moment, I'm trying to develop a game, a 3D platformer with a custom engine, including custom graphics tech. And today, I am very excited to discuss the evolution of GPUs. So our agenda today, the first thing I'm going to talk about is kind of the way that 3D rendering existed before the invention of GPUs. Then I will quickly explain the general 3D drawing algorithm that GPUs implement. And then I'll be discussing how each era of the GPU shaped the visuals of the games of that era. And so you can see the eras here, and we'll be getting into them. Just some disclaimers. This is mostly a talk that will be focusing on the PC space with some references to game consoles. This is not a talk that will be talking about the graphics chips in like iPhone or Nintendo Switch or whatever. And details have been simplified to protect the innocent. GPUs are mean in their complications, and so this talk will not have like every last detail of everything. This is a talk whose point is to try to convey to you guys the way in which the affordances of the GPUs of a certain era shaped the way those graphics looked. So, first thing we're talking about, the pre-hardware acceleration era, pre-1995. So the earliest 3D games on PC, you didn't have GPUs, so you had to use the CPU to draw the graphics. And this just sucks. CPUs are very poorly designed for the task of graphics rendering. The reason why is that there are usually many individual elements that need processed, like vertices or pixels, and their processing can be done independently, like theoretically, but the CPU operates in a serial manner where it does one operation, then the next one, then the next one, especially in this era before like multi-core CPUs. And so even if you were trying to write a program that literally just drew a 320 by 200 blank screen, like it just drew all red pixels, that would still run slowly because that's just so many memory accesses that the CPU has to do. And then even if you're very clever with your CPU rendering programming, your CPU still has to render the rest or run the rest of the game. You know, your AI, physics, input handling, network handling, reading from disk, like all those things have to happen sharing the same budget of time that graphics uses. So as an example of like the way things were back then, this is a benchmark that I found that benchmarked Quake from 1996 with a CPU called the Pentium 200, which is not even what people would have really had at the time. It's a CPU that was released 12 days before Quake. It was very expensive. So this is a very favorable benchmark in terms of the PC is really souped up. So at 320 by 200 resolution, the game runs at 46 FPS. So can't even get to 60 with this super expensive CPU. And then as soon as you bump it up to like an actually decent looking 4:3 resolution, like 480p, you're dropping all the way down to 17 FPS. And this is Quake we're talking about here, you know, made by the guys at id, you know, John Carmack. Like, they're doing every single trick in the book. Things are super duper optimized, but like even this really optimized program just can't get fast while it's using the CPU for rendering graphics. So it quickly became obvious that some sort of secondary computer chip, some kind of acceleration hardware would be required to help graphics out. But before we can talk about the hardware itself, we kind of have to talk about the way that this hardware would be designed. Because you see, if you're doing graphics rendering on the CPU, you're free to choose whatever scene representation and rendering algorithm you want. But if you're going to design a piece of dedicated hardware that's supposed to be used by like any game, you need to kind of come up in advance with an algorithm for doing the drawing that the hardware can implement. So real quick, the way that we represent scenes in this world is we have objects that are represented by a list of triangles. So like these triangles exist in 3D space and they like form surfaces, and the surfaces are detailed using 2D images called textures that are applied to the surfaces. And then these surfaces are optionally lit using lights that are either represented as like individual points in the scene that light comes out of, or lights can be represented by just a direction. Because for example, like the sun is like millions of miles away and its light rays are all coming from the same spot approximately, so we can approximate that by just saying, okay, yeah, the sunlight direction is that way or whatever. That's our scene representation, but then in order to actually draw our scene, the pipeline we do here is we take those triangle meshes that are represented in their own local coordinate system called model space. They're transformed into screen space by doing a matrix multiply. It's not important that you get to that you understand the math, but what's important is that you know that it's like, okay, each vertex requires a matrix multiply. When those triangles are transformed to screen space, they're then tested against each pixel on the screen to determine the coverage, and then each pixel that's covered has its color computed from the texture and lighting data that were fed to it. So of all the steps, of the 3 steps in this pipeline, the most expensive one, obviously, is the pixel processing step. There are more pixels than there are vertices, and you have to do texture sampling, and people wanted to do this thing called texture filtering, where like you sample the texture multiple times per pixel to get a nice like smoothed out average result. So in response to this scenario, enter 3DFX. They manufactured the Voodoo 3D accelerator chipset. And just as an aside, back in this era, we didn't even call these cards GPUs. They were typically referred to as 3D accelerators. So I'll be using that terminology for just a minute. So they made the 3D accelerator chipset by Voodoo. Just like today, hardware manufacturers buy the chipset in order to like make the full graphics card, like how today you might buy like an MSI RTX GPU or something. Pictured on screen is the Diamond Monster 3D, which was the most popular Voodoo 3D graphics card at the time, according to my research. And just as a rough comparison, this is about like what the PlayStation 1's GPU is capable of. So let's go over the responsibilities of the CPU and the accelerator. The CPU, every frame, has to transform and light the triangles, and then send those transformed triangles to the accelerator every frame, and then set up the state of that accelerator, which is stuff like what textures are we using, what's the fog density, where are the lights, what's the camera frustum like what's our aspect ratio, things like that. And then the accelerator is only responsible for rasterizing the triangles, that is determining the pixel coverage, and then applying the textures to the pixels while taking the lighting into account. So going back to our Quake example, and adding an accelerator, and benchmarking at 480p again, remember with the CPU alone, that got 17 FPS. But as soon as we add the DM3D, we go all the way up to 39.3 FPS. If you take a look at the frame times, that's a 56.8% improvement. And keep in mind, at this point, the CPU is still doing half the graphics work. The accelerator card is only handling rasterization and texturing and lighting. The CPU is still doing all of the geometry work. And just as an aside, something I found that was just completely wild to me, just in my research looking at old forums from the 90s, gamers at the time thought that 12 frames per second was acceptable for single player. And I mean, just wow, like they were suffering back then, like holy moly. Here's a side-by-side comparison. On the left, we have the CPU-rendered version of Quake. On the right, we have the first GPU or accelerator card rendered version of Quake called GL Quake. Aside from the right image being too dark, which is just an artifact of GL Quake being programmed wrong, you can see that there's a higher color depth, like there are more shades of colors. The textures are higher resolution. The textures are filtered. So like here, these like bolts are super duper pixelated, but over here they look very smooth and like rounded out. So in addition to the graphics card, making the game run faster, it's also making it look better, like at the same time. And that basically covers the very first era. Triangle rasterizers don't do very much. And rasterizing triangles and shading the pixels is only half the battle. Moving into the next era, hardware transform and lighting. The other work that has to be done, like I said, you have to transform the triangles into screen space, which is a matrix multiply by each vertex position. Then you do the lighting, which in this era was typically an additional dot product per vertex per light source. Just like the pixel calculations, these vertex calculations are all independent of one another. Like it doesn't matter which vertex is processed first or last. And so it's something that can be very easily parallelized by the hardware. So just like pixel processing before it, vertex processing was the next clear bottleneck that the GPU should accelerate. So in 1999, NVIDIA released the GeForce 256. This is the first graphics chip to support hardware accelerated transform and lighting. It is also the time where the term GPU comes into existence. This is a term that NVIDIA marketing comes up with to describe like graphics processing units. This is no longer just a dinky little triangle rasterizer. This processes all the graphics. It added an additional texture type called cube maps, which, like, if you know, you know. And the N64 had a comparable GPU. The N64 had very basic hardware transform and lighting capabilities, and that's why N64 was actually more powerful than PS1, or at least one of the reasons, but that's a bit of an aside. Moving on to the responsibilities of the CPU and GPU in this generation. So previously, the CPU would transform the triangle vertices and send them over. Now, the CPU provides the model space model, like the vertices in the local space of the model. It provides them ahead of time to the GPU, perhaps on level load, perhaps on game starting up, and then every frame, to position and rotate and scale the objects in the scene, the CPU can just send a transformation matrix for every object every frame. And this is really great because even at their most unoptimized, transform matrices are 64 bytes. And just for reference, like if you were sending triangle data that only had position data per vertex, you would exceed 64 bytes as soon as you sent 6 triangles over. So basically in all cases, it's a win to send the geometry to the device in advance. And then for the GPU responsibilities, the GPU does the matrix multiply of each vertex by the transformation matrix. It computes the per vertex lighting, and then does the same rasterization and texturing and lighting it was responsible for per pixel, while accounting for the vertex lighting that was computed in the previous step. So for my example for this, I'm actually going to use Half-Life in its expansion, because the original Half-Life's game engine, Gold Source, is actually a fork of the Quake engine, specifically the GL Quake game that I just showed you before. That's a 1998 release. Blue Shift, its second expansion, comes out in 2001 and actually requires hardware transform and lighting support in order to facilitate massively increasing the triangle counts of objects. So here's a screenshot of the shotgun from Half-Life. On the left, we have the original shotgun, and on the right, we have the hardware transform and lighting enhanced shotgun. Now, obviously, their design is different, but what I would like you to notice is that the left shotgun is basically like 6 or 7 rectangular prisms stitched together and then like a little cylinder at the end. Like, details are not being articulated because the polygon budget is so tight. But as soon as hardware TNL is introduced, we can have this like bridge thing with like these holes. These holes are actually articulated geometry like in there. This grip is like actually jutting out a little bit from the side. The arm and the hand are more detailed. So just like the geometry detail really gets to explode at this point in time, because now the GPU is actually handling the geometry instead of making the CPU do it. And that's basically the advantage of this era. So the next era is when we introduce programmability. At this point, GPUs have tackled the 2 big bottlenecks in the triangle rasterization pipeline. But the problem is that the way that the GPU operates on its data is fixed function. There are maybe a few dozen ways you can configure the pixels to be processed, and maybe a few dozen ways to configure the vertices to be processed, and these are pretty high estimates. But at the end of the day, all games that implement renderers that use the GPU are going to look kind of samey because they all have the same fog model available to them, they all have the same lighting model available to them. You can't do anything special with the vertices yet. And so it was highly desired by developers at the time to be able to specify what happens in the vertex and pixel stages, just like with code, like anything else. They really desired it, but unfortunately they would have to suffer for a little bit longer. NVIDIA and ATI both had a go at doing programmability on their GPUs, but the former only supported vertex processing, the latter only supported pixel processing, and if you wanted to ship a game that took advantage of both, you'd have to have 2 separate render paths in your code, like one for NVIDIA's way of doing it and one for ATI's way of doing it. It was just a nightmare. I'm not going to consider these GPUs to compose their own era, but let's just move on to 2003, when the GeForce FX series of graphics cards finally release, and these introduce the concept of vertex and pixel shaders as we know them today. Code that defines what happens to each vertex and to each pixel. This offers some performance benefits, but it also enables some effects that would have been impossible before. So I think the easiest one to explain is per pixel lighting. Back in the day, you would evaluate the lighting per vertex. Each vertex would have a vector associated with it that is the average of the face vertices of the triangles that it is like a part of. And so you evaluate like how closely that vector is pointing towards the light, and then you interpolate that lighting result across the surface of the object. And that works out okay, but you can get directional artifacts, and the lighting is, you're just not getting a lot of sample points for a lot of accurate lighting. But now you could just literally write a pixel shader that's like, yeah, I'm a pixel, I know my world space position, I know where the light is, do the dot product and give me my lighting. And so now the lighting can be a lot more smooth because it's per pixel. And another thing is that this is like the Xbox 360 era of graphics. Like the Xbox 360 had programmable pixel and vertex shaders, and I believe was the first console to have those. As my example here, I have the original Portal, which, if you don't know, can actually run in DirectX 8 mode and have way worse graphics. So on the left, we have Portal that does not use programmable shaders. On the right, we have Portal that does use programmable shaders. You can see how on the left, the portals are just like a simple oval color texture with like a mask on top of it to cut away the center. But with programmable shaders, we can now add like 2 layers of scrolling noise that kind of eat away at these textures and give it that wispy, unstable appearance that is so characteristic of the way portals look in the Portal games. So that's programmable vertex and pixel shaders. I need to also talk, though, about the extra shaders that sucked. Okay, so like, just really quick, there were 2 extra kinds of shaders that tried to be introduced before the next real era of GPUs came around. These were called geometry shaders and tessellation shaders, and they both tried to solve basically the same problem. Like, the problem being, we wish that there was a way to have lots and lots of detail in the geometry close to the camera, but not very much detail far away from the camera. But these were just not implemented super well. These were implemented in a way that was difficult for developers to take full advantage of, and they weren't very flexible, but they were still capable of doing some pretty impressive things. So like, here's my example of tessellation shaders. This is a benchmark program called Unigine Heaven 4. It's actually from 2011. This is like a benchmark that was developed to showcase DirectX 11 technology. On the right, we have the DirectX 9 version that does not have these extra shaders. On the right, we have the version that does have the extra shaders. And you can see that on the right, the GPU is able to procedurally subdivide like the cobblestone road and like actually articulate the individual stones. On the right, you can very, very clearly tell that it's like flat geometry with like stone texture applied to it. But what's like cool about these shaders, or at least what was appealing about them, is that like the game uploads, this low resolution geometry to the GPU, but then the shaders on the GPU automatically generate this based on like the camera distance and stuff. Like way out here where there's no detail, it's probably the same level of detail and geometry as like what's over here in this part of the image because it's not close to the camera. So anyway, that's just like my brief aside about geometry and tessellation shaders before we move into the next era and the truly exciting era, compute shaders. So for a while, game developers knew that further programmability of GPUs was the future. GPUs had already implemented what is known as a unified shader architecture. And what the hell does that mean? Basically, way in the past, like in the hardware TNL days, the vertex processing and the pixel processing would actually have different dedicated hardware for those sections. So like you couldn't use the pixel processing hardware to do vertex processing work. But unified shader architecture means that all of the sort of execution cores on a GPU are generic and are able to execute any kind of code. And this is important for load balancing. Like maybe you have a scene that is actually vertex heavy. Like, maybe you're rendering a shadow map, and so you're not actually running a pixel shader that does very much work. Well, you're going to be vertex bound, and it would be sucky if the GPU just like had more pixel cores than it had vertex cores, and so that workload like would just never be balanced. No, having unified shader architecture means the driver can balance based on what work is needed at the time. But because of this, you might think that you should be able to just program the GPUs to do whatever because they're already very generic. And in fact, this was possible as of 2007 with NVIDIA's API called CUDA that they released for the scientific computing community that was basically like, hey, do you have a parallel workload? The GPU is this parallel machine, like just write code for it. Vertex and pixel shaders are dispatched, which is to say the invocations of a vertex and pixel shader, like the number of invocations depends on the number of vertices, the number of pixels. But programmers were like, well, what if I could just say I wanted 64 copies of this shader? Like, what if I could just say I want like 128 by 128 block of like shaders executing? And that's what compute shaders enabled. So in 2009, DirectX 11 comes out and introduces something called the compute shader, which allows programmers to specify arbitrary work for the GPU to execute. This is an amazing godsend because there are so many workloads that are parallel, like workloads where the order of operations on the elements doesn't matter, and literally any workload that meets that requirement can be put on a GPU thanks to compute shaders. So that's just like super exciting. There's not really a good GPU to represent the introduction of this functionality because API support was ultimately the blocker in terms of being able to do programmability like this. And then PS4 and Xbox One were the first consoles that had true compute shaders. I want to say PS3 may have had a version of compute shaders, but the PS3 is really hard to understand. I can't really like say anything to that, but I know for sure PS4 and Xbox One had compute shaders. But crucially, in contrast, or I guess in comparison to the geometry and tessellation shaders I discussed beforehand, the compute shaders can do any of those things. Like, compute shaders can generate geometry in the same way that geometry and tessellation shaders can, and they can also do all kinds of other things that are important. So, like, one thing that you guys are probably aware of is the fact that games don't draw what isn't on screen, right? And the way that that works is, you know, the game knows the 3D volume that represents where the camera can see, and the game knows the bounding boxes of all objects. So you can just test the objects, bounding boxes, against the volume of the camera, and if it's totally outside the volume of the camera, you know that it can't show up, so you know you don't have to draw it. And, you know, typically, or traditionally, that would be implemented on the CPU. Like, before you submit the drawing commands to the GPU, you would be like, okay, is this guy in the thing? Is this guy in the frustum? Is this guy in the frustum? In a serial manner. But now you can just write a compute shader that does this for you, as well as all these other things, including GPU-driven animations, which I've actually implemented, if anyone wants to talk to me about that later. But compute shaders just like, they just let you do anything. I mean, they just let you do anything. So I don't really have like an example for compute shaders, but like just so many things behind the scenes we're able to get more faster and more efficient because compute shaders just enabled so much flexibility. And that's basically it for the compute shader era. At this point, things are looking great for GPUs. Vertex and pixel shaders can be as complicated as you want them to be. Compute shaders have arrived to allow you to move even more giant chunks of work to the GPU. And in the intervening years, graphics programmers have become so skilled at cheating with the existing techniques that games begin to approach photorealism, which is why now I need to take a brief aside to talk about a little thing called ray tracing. So up to this point, what I've described is a rendering algorithm called rasterization. And just to cover it again, we transform the triangles to screen space, compute the pixel coverage directly, and color them in. This is very, very fast. In ray tracing, you take your camera position and like the frame buffer you want to generate, and you shoot one or more rays through the pixels of the image you're trying to generate. These rays bounce around the scene, simulating real-life light transport, eventually converging to the final color of the pixel they were shot through, and producing an extremely beautiful and accurate result. But as you might have guessed, this is extremely slow. And even though ray tracing is actually an older algorithm than rasterization, ray tracing has always been like the holy grail of real-time computer graphics because it is just so slow, but it's so accurate. And like, if only we could trace rays in video games, wouldn't that be like so awesome? And it would be especially awesome because the photorealistic graphics that I talked about before are only possible by using these techniques that actually simulate ray tracing. And 1 second to take a drink. Things like dynamic cube maps for ray tracing less dynamic reflections, shadow maps so you don't need to use ray tracing for shadows, and the big one, light maps and light probes for doing global illumination and like the way light bounces around a scene without ray tracing. And this last one is a big one to note because when you have a data structure like light probes, like if you're working in Unreal or whatever, if you've ever worked in Unreal, you probably know that like, okay, you moved some objects around in your scene, but things don't look right until you rebake the lighting, and that can take a long time and really interrupt your iteration time. Like you're trying to be creative and like move stuff around and get your level built, but you're having to constantly wait to see what the actual effects of your changes are. And this really sucks, obviously, but ray tracing could solve all these problems. So in 2018, NVIDIA releases the RTX 2000 series GPUs. These GPUs are the first to have dedicated hardware cores for ray tracing. They introduce an entire separate rendering pipeline for doing ray tracing. Modern console GPUs are technically comparable, but their ray tracing is kind of bad. So like it's great that we have ray tracing now with these cards, and like great, that's going to like miraculously solve all of our problems. But even the most expensive modern RTX card can't hit 60 FPS in a modern RT game with everything turned up. At least not without a little bit of help. So let's talk about the other thing the RTX 2000 series GPUs added, something called deep learning supersampling. This is a technique where you can take a lower resolution rendered frame and upscale it using neural networks to a higher resolution. So this came out in tandem with ray tracing for really obvious reasons. You can't trace very many rays, even with hardware acceleration, without things slowing down. So what you can do instead is just render the game in a low resolution and then use deep learning magic to upscale to the resolution you actually want to play at. And, you know, I have some misgivings with this technique, but like for what it's worth, I played through Control, a great game, with this. You know, I had ray tracing on, I had DLSS upscaling, and it looked just fine. And DLSS was originally for upscaling, but it's actually now having some really other awesome features. DLSS can actually generate every other frame in the render stream for you. Your game still needs to be natively hitting 60 FPS, or you can have input latency problems, but it's cool that that's like an option for higher frame rates. And then it also has this really interesting thing called ray reconstruction, where like the rays that your program chooses for ray tracing can be changed into better rays that contribute more light because of the information that DLSS gives you. So that's basically what all of the modern graphics card features are. There's one last thing I just want to mention real quick called mesh shading. I just want to mention that it exists. It's basically this shader stage that replaces the vertex processing part with a compute shader. So it's like, what if we could have a compute shader directly feed the rasterizer? I just wanted to mention mesh shaders exist. I don't know enough about them to really like cover how they work, but you know, you can Google mesh shaders. They're pretty interesting. There's some cool demos you can find out there. Here's my ray tracing example using the only app that we have for ray tracing, I guess. This is obviously Cyberpunk 2077. On the left side, we have the game running maxed out, but without ray tracing. So like all the bells and whistles are turned on, but this is still rasterization graphics. And on the right side, we have the ray tracing graphics. The differences in quality are subtle at this point, but you can see things like this piece of wood is getting the light, the red light that it doesn't get over here that it really should be receiving. And like underneath the car here, there should be a really dark shadow. Like the ambient light should be really occluded by the car, which it correctly is in the ray trace scene. You can see it on the hood of the car here. The reflection of the neon sign is a lot more detailed and accurate on the right-hand side here. And so, yeah, like those are kind of the visual upgrade benefits, but I want to reiterate the fact that like the real benefit from the game designer's perspective is like not having to worry as much during the level design process of like, oh, I gotta wait for this thing to bake again, or like, oh, what's this gonna look like when we finally export it to the real engine? I don't know, like, you know, like these things that ruin your flow states could be solved with ray tracing. And why do I keep saying could be solved? That's pretty like, that's a bad omen, isn't it? Well, there are a couple elephants in the room regarding modern GPUs, which you're probably aware of. Over the past couple years, GPUs have gone from being expensive computer components to being super luxury items that cost like over $1,000 for like one of them. And that's for a number of reasons, cryptocurrency, uh, LLM worship, and thinking that AI is going to solve all our problems, general financial speculation and scalping as a result of those previous two things. So, like, ray tracing adoption has been stunted by these market conditions, which means that development from the application side can kind of stagnate because developers still want to release games that support hardware that doesn't do ray tracing. But obviously, if you're doing that, then you're not getting any of the production benefits I just talked about, because during production, you're still having to worry about that the light baking stuff, because you're still having to ship on GPUs that need light probes and light maps and stuff. Um, and just like as an aside, right now we have like apps that give you noisy, blurry images, even with their upscaling. If your app isn't doing what is called path tracing, where you do like, the full ray tracing I described, where you shoot rays out of the camera, that's path tracing, at least in the current industry jargon. There's another approach called hybrid ray tracing, where you like rasterize the triangles first, and then in your pixel shader, you do ray tracing for extra effects like shadows and reflections. I've also implemented this if anyone's interested. But like in an app like that, you're obviously having even more compromises and you can't get as many benefits from ray tracing. So modern GPUs are in kind of a precarious state. I do think that they're exciting and their new features are cool. But yeah, that's basically the state of modernity. And that's basically the history of GPUs. Thank you guys so much for listening to my talk. I will send my slides to anyone who wants them. So you don't need to like take a picture of this necessarily. These are just like the references for my research for this talk. And then I have my blog, my Blue Sky account, and my YouTube, where I actually have my 2023 GDEX talk uploaded, and where this talk will be uploaded to, if any of you want to see it later. And like the slides will also be posted in the description of that YouTube video. But that's it. That's my talk. We're now open for Q&A. So who has questions? Yeah. More programmability. Like basically that's the prediction you can always make. So like I just alluded to mesh shaders. Like I guess I'll talk about that now. Like you could have a compute shader run that generates some geometry, and then afterwards run a rasterization pipeline that draws the geometry. Sounds great, right? Well, the problem is the compute shader has to write all the way out to the main memory of the GPU, and then the draw call is going to have to read all the way from the main memory of the GPU. Whereas if these two things were part of the same unified pipeline, they could maybe be using some shared memory that's a lot faster. So mesh shaders are this way to take the old vertex shader pipeline and instead basically just let you use compute shaders to generate whatever geometry you want. So like vertex shaders were already programmable, and mesh shaders are basically allowing you to do all the same things, but with even fewer restrictions. So like I guess my prediction would be like maybe the ray tracing APIs become more open and less closed down secret sauce like they are right now. But yeah, prediction, more programmability, more developer freedom. Anyone else? All right. So the question was, what's the best way to jump into learning GPU programming and shaders? So there's a graphics programming Discord. There's a website called learnopengl.com that I used, but I have to shamelessly plug my talk from 2023, where the entire topic was how to get started as a graphics programmer. If you look up my YouTube, you'll be able to find that talk. I explain the 3D rendering pipeline. I explain resources for beginners. I explain the differences between types of graphics APIs. There's a YouTuber called Ace Rolla. If you don't already know about him, he's the best. Yeah, everyone knows about Ace Rolla. Simon Dev, Coding Adventures. Yeah, those are all my suggestions. Anybody else? Yeah.
there any news on how to make that?
Yeah, talk about, so the question was like, is there a way to make bidirectional reading and writing from the GPU faster for like, I want the GPU to generate some data and then the CPU to read it back. So talk about another holy grail of graphics, basically. Like, the PCI bus is slow. That's kind of like the main bottleneck in graphics programming, and a lot of what you're doing is trying to avoid any communication. You probably are already aware of the trick of like just use the last frame's results, because if you use this frame's results, you're going to have a stall on the CPU side before you're able to continue your work. So I don't really have a magic bullet here for you. Really, it's like try to find any other way to solve your problem besides reading data back from the GPU. And if you absolutely have to read data back from the GPU, read back the last frame's data. And if you absolutely need this frame's data, then like, I don't know, start praying or something. Like, I don't have an answer at that point. I'd be really curious to hear more about your use case, but reading back from the GPU to the CPU is just a cursed, crappy thing. Yeah, I'm online. I mean, if you...
connect to the internet. Sure, YouTube video if you want to see.
I mean, sure. Am I even online? I've got to go to the network login page. That's so exciting. And I didn't type it in right. Yeah, so I don't know how you want to send me a link, but I'd be happy to try to pull it up here. Am I looking at my title, maybe?
Yeah,
Were there any other questions, by the way? No? All right.
look for Isle of Disaster.
Oh, you're the Isle of Disaster guy. We've spoken before. We've spoken before. This thing?
Do the second one. Although both of them are. The top one was 3.
Well, now I know your use case. So you're doing lava flow simulations and compute shaders, is that what you're telling me?
Yeah. And so a lot of this is all done in compute shaders, and then actually, I guess the next side you can see
The one that's like here?
Yeah, you'll see also. You probably want to fast forward a little bit. There's somewhere it actually is burning trees and stuff like that.
Okay, here. The lava's flowing at this point. You can see all the pixels.
Well, it's actually high res. I don't know why it's.
I know, it's just crappy internet. I'm just making a joke.
I want to mute it. But yeah, in order to burn the trees, I need to get the information back from the GPU in order to know which trees to basically.
Yeah, because the trees are objects on the CPU. Yeah. I'd have to think more about it, basically. This is definitely like not an easy or trivial problem. Like I said, reading back from the GPU is just like bad. Like, it's just not a well-supported operation, and that kind of just comes down to the way that desktop computers are architected. This would not be a problem if you were on console or on like the new MacBooks or something with unified memory. So yeah, unified memory, if that ever comes to PC, that'd be a crazy thing. I wouldn't predict that though. Yeah, it would be so nice. It would make our lives so much easier. But yeah, all I can tell you is you can hide the latency by just reading the last frame's results. Like, don't wait for this frame's results. That can give you back all your performance at the cost of 1 frame of lag on that effect, but it can be worth it. It can be worth it. That's like my one thing.
That is what I'm doing.
Okay.
So I'm able to hit 60 frames a second, but it's.
Yeah. Yeah, well, again, sorry I've got no magic bullet for that one, but... Yep. Thank you guys so much for coming to this awkward time slot. 12 frames a second, and we liked it.
I was in that